Hi ladies and gentlemen, another quick video just looking at some of the content associated with Rolle's theorem and the mean value theorem. So unlike the more applied problems, for example the related rates problem that we were talking about, this is really focused on more of the ideas. And what I want to do is explain to you what you need to understand, some ways to kind of think about these things, and then things you don't need to understand or worry about. So what I did was, this is from Wikipedia, I just went in, typed in Rolle's theorem, and this was part of the explanation. I copied and pasted it here. I wanted to let you know that I took it from Wikipedia. But this is the statement of Rolle's theorem. It says if we have a real valued function f, and it's continuous on a proper closed interval, it's differentiable on an open interval, and the endpoints are equal to one another, so the outputs of the function are equal at the two endpoints of the closed interval on which the function is continuous, then there exists at least one point inside of the open interval. So there's one input value inside of the open interval such that the derivative of the function is equal to 0. So, and then there's a little bit more about this. The Rolle's theorem is used to prove the mean value theorem. You'll see that in your work. And so this whole concept is, I want to differentiate it for what you need to know and what you don't. So this result is reasonably obvious, you would think. So if I said, hey, look, we have a function that's going to be at value A and value B, it's going to be the same output. Well, if the function's continuous and it doesn't really matter what I'm doing in here, then what the theorem says is that there's some point in here, some point in between A and B, some point C, for example, where the derivative of the function is equal to 0. Now, there could be several places, right? We have several places here where the rate of change is 0. I've kind of drawn an oscillatory function. It has lots of places. The theorem says there's at least one. So one very interesting and important way to think about these theorems is to start asking questions about why are the hypotheses, why are the requirements in place? Why does this function have to be continuous? Why does it have to be differentiable? And we start thinking about counterexamples. So I would offer to you that anytime you learn something new in mathematics, it's worthwhile to think about the counterexamples for the theorems or for the lemmas or whatever it might be. So counterexamples are a great way to learn about why things work the way they work. So first of all, let's say the function is not continuous. Can we come up with a discontinuous function that doesn't satisfy Rolle's condition? Well, we certainly can. So imagine here's our A and here's our B, and we could come up with a function very simply that just increases up to here and then increases like this. So this function's discontinuous. It has some constant positive slope. The slope is never 0. This is an example of a counterexample on why we need the hypothesis of continuity. Now, when it comes to the closed interval AB for continuity and the open interval AB for differentiability, I would say leave that. You can certainly explore it and think about why that would have to be true, but those are more advanced topics that are really important for real analysis, if you take a real analysis course. Similarly, you do not need to prove Rolle's theorem. You just have to have an understanding of what it says. And what it says is pretty straightforward. If you want to learn about writing proofs, mathematical proofs, then that is something you can do in more advanced math courses, and you would again end up leading towards real analysis, which is where a lot of these kinds of results end up being proven. So how about the differentiability requirement here in Rolle's theorem? Let's think about another example. I'm going to shift over to my red pen here. So I have an A and a B. Now this one's a little harder for me, right? If I have to have a continuous function, so I have to have a function that somehow is together, I don't see how I'm going to end up with something that doesn't have places where the derivative is equal to 0. Even if it isn't differentiable, let me draw another one. What if I had one that came up like this and then had a spike like that and then came down? So the function's not differentiable here. We have that cusp type of an appearance. But still, I have several places where the function would satisfy Rolle's theorem. Well, but the cusp gives us an idea of how we might make this work. We can come up with a counterexample by considering, and I'm going to come back up here and do it. So I have some endpoints A and B. What if I just took my function up like an absolute value and drew it just straight like this? So I'm looking now at the gray function. Well, now I have a function which has some kind of positive slope here and negative slope here, and there is no definition for the slope at the cusp. Well, I don't have any slope that's equal to 0. I don't satisfy Rolle's condition because I have a function that is not differentiable everywhere. So this is the idea about how we think about these things. An extension of Rolle's theorem, it's actually a direct and straightforward extension, is the mean value theorem. So what the mean value theorem says is, and again I took this from Wikipedia, it says the theorem states that if f is again continuous on a closed interval and differentiable on the open interval, then there exists some point C inside of the open interval AB such that the tangent line at C, in other words the derivative, is parallel to the secant line that goes through the endpoints. So let's draw this picture. Pictures generally help. I have some point A and some point B, and I have a function now that is not required to start and stop at the same value. And what I'm going to do is just have it start and stop there, and I have some function that goes like this. And what it says is, what the mean value theorem says is, if I consider the secant line that connects these two points, if I look at the slope of that line, the mean value theorem says there's at least one point in here where the slope of the tangent line, the slope of the derivative, is the same. So it turns out that this is a really straightforward result from Rolle's theorem. Let me give you an example. Let me move this up and make it easy to see. I'm going to shrink this down just a little bit. Okay, so here is a graphic, for example, for Rolle's theorem, where we see we have this function that satisfies the conditions. It's continuous on the closed interval, it's differentiable on the open interval, and we can see there are several places where the slope would be equal to 0. The endpoints of the function both touch on the horizontal yellow line, so they both have the same value over here that they evaluate to. So all the mean value theorem is this. If I take the idea of Rolle's theorem and I simply rotate the function, as long as I maintain it as a function, obviously I could over-rotate it, and now I have something here that's no longer a function, right? For each input in here, I have actually two outputs. I no longer satisfy the vertical line test. So let me change it back. But as long as I continue to have a function, as long as I continue to have something that satisfies the vertical line test, then what the mean value theorem says is there's some point in here, at least one, where the rate of change, the derivative, is the same as the secant line that connects the two endpoints. And it's very easy to see with this demonstration why that would be true. Again, you don't need to prove these results. You just need to have a clear understanding of what they're saying. The reason that these types of theorems are important, sorry, let me go back to that graphic. The reason that they're important is because these are the types of results that allow us, when we pursue advanced architectures, for example, machine learning, when we're trying to solve a machine learning optimization, we're trying to get as close to minimizing the objective function as we can. These are the types of results that allow us to say, hey, you know what? I know that I can make progress. I know that I can continue to improve. I know that I have rates that are available to me, and those results are provided by things like the mean value theorem. the intermediate value theorem, the extreme value theorem, these theorems which are part of basic calculus but have applicability way beyond the basics. Anyway, a little bit of an intro for you. Have a good week.